So for this section, we are going to talk a little bit of experiment 5. That is about recycling aluminum. In this experiment, we are going to make reference to alum, which can have a charge of +1 or +3. Also, it is named alum because it belongs to a general family of for crystalline. In this section, we are going to emphasize in a kind of aluminum called potassium aluminum sulfate, known by its empirical formula Kal in parentheses SO4 close parentheses 2. Also, we are going to use it with 12 molecules of water, also known as dodecahydrate. Then we will synthesize this compound by using an accurate ions in an aqueous solution. All this process is going to be exciting because we are going to witness physical reactions as well as chemical reactions. And also in chemistry, aluminum foil is always oxidized to obtain aluminum ions. On the other hand, the solution obtaining the potassium aluminum sulfate, when it evaporates, we will see the formation of crystals from the compound mentioned before. After we finish with this experiment, we will keep the remaining of aluminum because it's one of the metals that is very good to conserve because it is considered a very good for recycling. The purpose of this experiment is to calculate the percent yield by preparing a sample of potassium alum from aluminum. And this we will use it by the formula that is the actual yield divided by the theoretical yield times 100, and we will get the percent of this compound.
I will be going over the procedures for experiment 5. After you've made sure that you are wearing the proper safety equipment, you will weigh out 0.5 grams of small pieces of cut aluminum scraps. These scraps will go into a 200 to 250 milliliter beaker. You will then take your beaker to the fume hood and add approximately 25 milliliters of 1.5 molar KOH solution to your beaker, making sure that you do not spatter the solution because KOH is very caustic. Once you've added your KOH solution to the aluminum scraps in your beaker, you will heat your beaker gently inside the fume hood using the lab's hot plates. Heating the solution will evolve H2 gas. Heat the solution until the aluminum has dissolved completely and no fizzing can be heard from the beaker. You may need to add distilled water to the solution if it drops below half the original volume level. Do this with a wash bottle to bring the solution back up to about 2/3 of the original volume. Using tongs, remove the beaker from the heating unit and return to your lab bench. Prepare a piece of filter paper by folding it into quarters and placing it in your short stem funnel and wet it with distilled water to ensure a good seal. Place the funnel over your beaker that you will use for collecting the filtrate. Pour the liquid into the funnel to collect the filtrate and rinse the reaction vessel 2 times with approximately 3 milliliters of deionized water, allowing these rinses to pass through the filter as well. Discard the filter paper, but save the filtrate for the next step. Allow the solution to cool for approximately 5 minutes, then place it in an ice bath to further cool it. Stir the solution continuously while adding 9 molars of H2SO4 until the pH paper shows that the pH is about 1 to 2. Lumps of AlOH3 may appear, but should redissolve. Heat gently and be sure you do not boil the solution until all of the AlOH3 dissolves. This should result in a clear solution. Remove the solution from the heat and cool in an ice bath for about 20 minutes to form the potassium alum crystals. Collect the crystals by vacuum filtering using a Buchner funnel and a filter flask. Transfer your alum crystals by swirling the liquid and crystals into your beaker and pouring the resulting suspension into a Buchner funnel while applying suspension with a vacuum aspirator. Transfer as much of the crystals as possible using a spatula and some of the filtrate. Break the vacuum by removing the hose from the side of your flask. Remove the funnel and pour the filtrate into a small clean beaker. Repeat this process to transfer the remaining alum crystals from the reaction vessel to the filter. Wash the crystals in the Buchner funnel using several small portions of your filtrate. Use a disposable pipette to slowly add 10 milliliters of cold methanol to the alum product. Do not attempt to collect any new crystals formed during this step. Remove the top part of the Buchner funnel and transfer the filter paper and crystals to a watch glass. Leave your crystals in a lab drawer to dry until the next lab period. In the next lab period, you will determine the mass of the alum crystals, correcting for the mass of your filter paper. Record the mass of your crystals in your lab notebook and transfer them to a glass vial, which you will label with your name, the formula, and the mass.
To do our calculations correctly, we're going to need some values that we've measured from around the experiment. We're going to need the mass of aluminium scrap, which is 0.5 grams, volume of potassium hydroxide, which is 24 ml, the mass of the watch glass and filter paper, the mass of the watch glass, filter paper, and alum crystals, and the mass of the alum crystals alone. This is how the balanced equation looks, and we're going to need this to get the relationships between the different compounds.
Now we're going to calculate the theoretical yield. Supposing that aluminum is our limiting reactant. So we are going to use the mass that we first started, that was 0.5 grams. Then we're going to use the molar mass of aluminum, which is 29.98 grams. Then we're going to use our balanced chemical equation to convert it to grams of KAlSO4 So we use 2 and 2, which is come from this and this. And our molar mass from this compound, which is 516.44 grams. Then as a result, we cancel out everything, getting our mass from KAlSO4 which is 9.57 grams. And our percent yield, we use this equation, that is our actual yield divided by our theoretical yield times 100. So our actual yield was 5.01 and our theoretical yield was 9.57 grams times 100, we get 52.4% of the aluminum scrap. Thank you.
Some of the sources of error could be by not heating the mixture long enough before cooling it down. Another one of them could be by spilling some of the mixture either while transferring it from one beaker to the other or by allowing the mixture to boil, because when it boils it starts to splash out of the container. The resources for this experiment were gotten from Dr. Mullen's handout for experiment 5, and I guess that's it.